Greetings everyone. Today we are excited to present our work on the role of polymers in energy storage and conversion for our polymer chemistry course. To start, what is a polymer? The polymer word itself comes from the Greek poly meaning many and meros meaning parts. Polymer chemistry is a study of these large molecules which are made up of repeating units called monomers. Polymers are foundational to modern life, driving applications in everything from technological progress and everyday convenience to environmental innovation and critically the energy sector. This simple visual illustrates the core concept, the progress of polymerization, where many individual monomer units chemically bonded together to form a long chain-like polymer. Need for polymer-based energy materials. Lightweight and flexible, tunable conductivity, eco-friendly and cost-effective, chemical and structure versatility, and lightweight, sustainable and customizable for modern energy devices. Our focus today is on their role in energy. We start with polymer in batteries. Here, polymers are incredibly versatile, acting as binders for electrodes, ion conducting electrolytes, and microporous separators. By ensuring structural integrity and enabling efficient ion transport, they dramatically improve a battery's safety, capacity, and overall life cycle. First, the polymer binders. Their job is to physically hold all the electrode components, the active material and conductive agent together. They are essential for maintaining the structural and mechanical integrity of the electrode as it expands and contracts during charging and discharging. They also ensure adhesion to the current collector. Common examples include polyvinyl diene fluoride, styrene butadiene rubber, and carboxymethyl cellulose, and last polyacrylic acid. Next, polymer electrolytes. These act as the medium that conducts ions, typically lithium ions, between the electrodes. They are a game changer for battery safety as they are often non-flammable and reduce the risk of leakage. In solid-state designs, they also help suppress the formation of lithium dendrites which cause shorts. We see them in both solid polymer electrolytes and gel polymer electrolytes. Third is polymer separator. The polymer separators are key safety components. They function as an electrical insulator that physically separates the positive and negative electrodes, preventing a short circuit. Crucially, they are a porous barrier that allows the ionic charge carriers to pass through. Some, like multilayered polyethylene separators, even include a shutdown mechanism that melts and stops ion flow if the battery overheats, enhancing safety. Examples include polyethylene and polypropylene. Examples are polyethylene, polypropylene, PVDF, and PVDF-HFP, polyimide. Fourth is redox active polymers. A specialized and emerging area is the use of redox active polymers. Here, the polymer itself serves as the primary charge storage materials in the electrodes, participating in reversible redox reactions. This allows for the development of organic batteries that reduce reliance on potentially scarce or toxic inorganic materials. Well known examples include polypyrrole and polyaniline. This diagram shows the integrated roles. The electrodes are separated by the polymer separator, which allows only the ion transport to occur as the battery charges or discharges. Examples and applications of batteries. First is consumer electronics, electric vehicles, remote controlled devices, aerospace and robotics, medical devices, and last, renewable energy storage. Moving on to supercapacitors. Polymers are again indispensable, used in three main ways: as the active electrode materials, as binders or as conductive additives, and as electrolytes or separators. When we used as electrode materials, conducting polymers like polyaniline, polypyrrole, polythiophene are widely used for charge storage through pseudocapacitance, a rapid Faraday process. They are valued for their high electrical conductivity, large specific capacitance, and enabling fast charge discharge rates. Examples are polyaniline, polypyrrole, polythiophene. Reaction mechanism: in these polymers, redox reactions involving doping of ions from the electrolyte stored charge. This is the source of pseudocapacitance. Next is polymer binders. Non-conductive polymers are used as binders to hold the active material together on the electrode surface. They improve mechanical stability and prevent detachment of active material during charge-discharge cycles. Examples are polyvinylidene fluoride, polytetrafluoroethylene, carboxymethylcellulose. Though they do not contribute directly to capacitance, they ensure the structural integrity of electrodes. Polymer electrolytes and separators. Polymers can form gel or solid electrolytes that allow ionic conduction while preventing electronic conduction between electrodes. These improve safety, flexibility, and operating voltage window. Examples: polyethylene oxide, polyvinyl alcohol combined with acids or salt. Next is polymer-based composite systems. One of the biggest advancement is polymer-based composite system. By combining polymers with materials like graphene or metal oxides, we create hybrid electrodes that leverage the polymer's high conductivity and the inorganic material's high surface area, pushing the limits of performance. The Ragon plot visualize why this matters. Supercapacitors offer a high power density, faster energy delivery, which is a key advantage over traditional batteries. This diagram shows the conducting polymers and their composites for supercapacitors. Examples and applications of supercapacitors: energy storage in electric vehicles, wearable electronics, hybrid capacitors, uninterruptible power supplies, energy recovery in public transportations, power smoothing for renewable energy systems. Next, we look at polymers in solar cells. A solar cell converts sunlight into electrical energy through the photovoltaic effect. The major benefit of using polymers is the potential for lightweight, flexible, and low cost devices that can be printed on large areas. This is what we call plastic solar cells or organic photovoltaics. Basic structures of polymer solar cell: transparent electrode, active layer, metal electrode. Advantages of polymer based solar cells: mechanical flexibility, simple fabrication, and suitable for portable or wearable electronics. Important conducting and semiconducting polymers. The active layer in a polymer solar cell uses specific semiconducting polymers. First is poly 3-hexyl thiophene. It is p-type semiconducting polymer. Its features are excellent light absorption in visible region, good charge mobility, easy to synthesize and process. Its major role is to transfer electrons to accepted materials. Second is polyphenylene vinylene. Early polymer used in organic solar cells, good optical properties and tunable band gap. Third is PCPD-TBT. Low band gap polymer absorbs more sunlight up to near infrared region, increases power conversion efficiency. And last fourth is PEDOT, improves interface contact and enhances device stability. This diagram shows the examples of donor and acceptor materials used in solar cells. Working principle of polymer solar cells. The process is elegantly simple. Light absorption by the polymer creates an excited state at the interface between the donor polymer and an acceptor material, for example, P3HT and PCMB. This excitation undergoes exciton dissociation, splitting into a free electron and a hole. These carriers then undergo charge transport to their respective electrodes, resulting in the generated electric current. The polymer is vital here, acting as both the light absorber and the charge carrier transporter. This is a visual representation of photovoltaic cell. Advancements in polymer solar cells. Research is rapidly improving OPV technology. Innovations include the use of non-fluorine acceptors for higher efficiency and perovskite polymer hybrid cells, which combine the stability of polymers with the efficiency of perovskites. Power conversion efficiency has dramatically improved from less than 1% to now exceeding 18%. However, key challenges remain, particularly the need for better stability under sunlight and air exposure. Our final application is polymers in fuel cells. A fuel cell is an electrochemical device that converts the chemical energy of a fuel, like hydrogen, directly into electrical energy. Polymers are essential here, providing ion conductivity and acting as the electrolytes, membranes, and binders that give the structure a lightweight and flexible nature. Types of fuel cells using polymers. First is proton exchange membrane fuel cell. Second, direct methanol fuel cell. And third, ion exchange membrane fuel cell. It uses hydroxide ion conducting polymers. Major polymers in fuel cell. The most common type is the proton exchange membrane fuel cell, which relies on polymers for proton conduction. The benchmark material is Nephron, a perfluorinated sulfonic acid polymer. It offers high proton conductivity and excellent stability, although it is expensive. Second is polybenzimidazole. It is used in high temperature PEMFCs up to 200 degrees Celsius, doped with phosphoric acid for conductivity. Advantages are works without humidification and more CO tolerant. Third is sulfonated polyether ether ketone, cost effective alternative to Nephron, tunable sulfonation degree adjust conductivity, better thermal stability and lower cost. Working principle with polymer electrolytes. The polymer membrane is the heart of a fuel cell. At the anode, hydrogen is converted to proton and electrons. The polymer electrolytes like Nephron is designed to selectively conduct the hydrogen ion from the anode to the cathode while blocking electrons and gases. The electrons are forced through the external circuit, generating power, and at the cathode, the protons, electrons, and oxygen combine to form water. The polymer membrane enables this critical proton transport and gas separation. Diagram shows fuel cell with membrane electrode assembly. Advancements in polymer-based fuel cell materials. Modern innovations. Composite membranes, Nephron plus inorganic fillers for enhanced stability. Non-fluorinated polymers, environment-friendly alternatives like polyacrylene ether sulfone. Ion exchange membrane, using quaternary ammonium-based polymers for alkaline fuel cells. Biopolymer-based membranes, cellulose blends for sustainable fuel cells. Challenges are durability at high temperature, cost reduction, maintaining water balance under variable humidity. Future focus: designing low cost, high conductivity, and eco friendly polymer membranes for next generation fuel cells. In conclusion, polymers plays a vital role in advancing all next generation energy devices due to their flexibility, lightweight and tunable properties. They enhance ion transport in batteries, improve charge capacity in supercapacitors, provide proton conductivity in fuel cells, and enable flexible, low cost solar cells. The future is focused on developing highly conductive, biodegradable, and nanostructured polymers, promising us cleaner, more efficient, and truly sustainable energy solutions. Thank you.